Hello everyone, October 17th. Alright, so today's goal, we do the challenge, and after that, we need to write the OND solution for the minimum difficult job. Okay, so the bottom up OND instead of ON squared D. Alright, let's do this one first. Count and say is a sequence of digit strings defined by the recursive formula. Count say 1 equals 1. Count say n is the way you would say the digit string from count and say n minus 1, which is then converted into a different digit string. And how you say a digit string is split into the minimum number of substrings such that each substring contains exactly one unique digit. And then for each substring, say the number of digits, then say the digit. Finally concatenate every sad digit. For example, the say-in and a conversion for digit string this will be 2, 2, 3, 3, 2, 1, 5, and 1, 1. Given a positive integer n, return the nth term of the count and say sequence. What do you mean by nth term? So this is n is 4. Huh? Wait, what? Is the way you would say the digit string from count and say, which is then converted into a different digit string. So count and say 4 is going to be count and say 3. The way you would say count and say 3. Okay, hold on. So we'll say 4 will be, you will say 3 will be, you will say 2 will be, you will say 1. So you say 1 will be 1. So count and say 2 will be the way you will say the digit string from count and say 1. So F2 is going to be 1, 1. F3 is going to be 2, 1. Right? So 1, 1 will be 2, 1. And F4 will be 1, 2, and 1, 1. Wow. I think I know what this one means. Pretty stupid, but alright. So what? We just go for it. We don't have the recursive because we can just go from 1 all the way to the end. And because if you recursive, it's going to be tail recursion, so there's no difference. And when we get it, oh, we have to go to the end because the nth might be different. It might be different. Seriously, it might be different. Yeah, it will be different. Okay, let's do this. Count and say n. Position 1, right? The nth, I think it's 1, 2, 3, 4. Oh, hold on. Oh, it's not the nth, it's the nth term. So just actually return this thing. Oh, okay. Actually, think wrong. What are you thinking? I'm thinking using group by. Right? Then we say Okay, if n equals 1, return 1, okay? And then s equals 1. Now I can do this. S equals 1, now I return s. Right. And then for I range 2, 2, and plus 1, for each one, we're gonna do group by s. Right? And then we say for kg in this, and then we can say length list of g, right? Length list of g, and then k. So we're gonna do with f string this thing. So this and k, right? And then s equal to a join. Then we'll return s. We don't have to test 1. Wait, 1, 2, 1. One, two, one. My bad. That might be slow, but it's all right. I can do all of them. I can do all of them. Yeah. 2018, that was the last time we did this. I call it O1 squared, right? Actually, no. We don't know how long this one is, so I'd rather not say. I'm just call it. All right, so this one's done. We go back to here. So we want to do solution number 2. Wait, this is solution 1. Okay, solution 2. This is a O and D time complexity solution from LeetCode. It seems like a 1D DP, but it also uses stack to simplify, to reduce the amount of computation. We use DP and temp, right, for the previous and current DP state. So DPI is the minimum of job difficulty, minimum of schedule difficulty from 0 to I for j for the j minus 1th day, right? And temp I is the mean schedule difficulty from 0 to I for the jth day. Thus, we are at temp I, right, we first look back at dpi minus 1. Right, we'll look back at dp minus 1. We say we take job I by itself, then the temp I shall equal to dpi minus 1, right? dpi minus 1 is the previous minimum, and then I want to do one more day at job I, at the 8th day. So I shall plus job difficulty I, right? So that's kind of the, wait, I feel like this is not right. Hold on. So the previous day, right, and the current day, yeah, this is right. To make sure I didn't go wrong in the beginning. All right, so that's, yes, that's right. Okay, so that's the beginning. And then we consider whether it is possible to group job I with any of the previous jobs. Right. So for each day, we maintain a monotonic decreasing stack, right, which stores the indices of the job with decreasing difficulty. We compare job difficulty I with the tail of the stack. If the tail is smaller, then we are certain that if we take all the job from stack minus 1, if, I'll take a look, if we include job I, if we include all the jobs from job stack minus 1 to job I, they will all have the same difficulty as job I. Thus, we update. Right? So they will have the same job difficulty, so we update. So we need to pop that. And when we pop it, we'll update, which means this, it will include this, right? That's what it is. We'll include it. So actually no, it's a DP2. Oh yeah, it's a DP2. So we'll say we'll include this job Why? Our current job has a higher difficulty, right? If it has a higher difficulty, then yeah, because it has a higher difficulty, it'll be wise that we use a higher difficulty. Yeah, that's the reason. And since it is, no, hold on. If the tail is smaller, then we are certain that if we include, if the tail is smaller, then we should not count then we should group, right, job stack -1, group job stack -1 with job I, right? Because when we group them, we only count it once. If I don't group them, we'll count this and we'll count this. We'll count it twice. Right? That's why we say it's bad. Yes, then we should group this with job I. Yeah, that's true. Because by doing so, we are not incurring more no, let me see again. J-pop. And then we'll say this one minus this. Oh, dp2j minus this. Oh. If the tail is smaller, then we shall group this with job I, right? When we are handling job I. So group all the jobs from this to job I, because they will all have the same max difficulty, which is job difficulty I. Right? And this also reduces counting, reduces the counting of multiple local high job difficulties. Right? Once we reach job stack -1, that is larger than, so it's smaller equal to, yes, larger than job difficulty I, right? So I hit something that's larger. What do we do when I hit something that's larger? Shouldn't we do that again? Okay, dp2i and dp2 stack. Oh, yes. Once we reach that is larger than job difficulty I, we have the possibility, right? We have the possibility to, should be there, we have the possibility to group this might reduce counting of high, yeah. We have the possibility to extend the day, right, from to extend the job from, we have possibility to include job difficulty I into job stack -1. Once both conditions are considered, we will have arrived at the minimum schedule difficulty for the current day at job I. Okay. So what we're going to do is, so dp shall equal to math.inf times n temp. We'll do temp every single time. So this is 0 day, right? Job schedule difficulty on 0th day. Okay, now I'm going to say for this in range D, right? I have the first day, or actually for K in range D, right? And then for I in range K to N, right? Because the second day you have to start from the second. The third day you have to start the third. Wait, why is that? Yeah, what is that? Yeah, why is that? Why don't we go start from the zeros? Because on, let's say the second day, right? A second day, you cannot start from the first because the first day has to start. Each day has to do at least one work. So after the first day, you must start. Yeah, so after after K days, you must start. K jobs must have been done. At least K jobs, right? Okay, so with this, now we say, can I say temp equals to 0 times n, and I'll have a stack is equal to this. Okay. Then we say temp I shall equal to dp I -1, right, plus job difficulty I, and this will multiply it by I larger than 0. Okay, now we're going to compare. We say while job difficulty I is larger equal to stack -1 job difficulty, right? When it's larger than this, then j equals to stack.pop, right? So this is current is bigger, so we can group, right? We say group jth job, group all jobs from j to I together, Then when you group together, then we say temp I shall equal to, when they group together, what becomes of temp I? Well, first of all, we need the minimum, because it could be the original temp I that's smaller. Or, now we're going to do is going to be temp j, which is the total difficulty up to j, right? But then we want to combine, so it has minus job difficulty j, but with plus job difficulty I. So that's that. So blah blah blah, we're all done. Now when we come out, we say if stack, which means that there's still something in the stack, and the stack minus 1 is larger. Then we'll say include ith job with the current with the stack minus 1th job. And say temp I might be minimal temp I, and then temp stack minus 1. Then stack.append I. Right, so blah blah blah, when we're done, say dp equals temp. In this case, yeah, we're creating new things. Yeah, I remember. Yeah, let's not do this. Let's say temp equals 0 times n. And we can save some. Just swap it. dp temp equals temp dp. Right, we just swap it. And once we're done, we're gonna return, because at the end of the day, right, the last day, we swap. So dp is the last day, so it's dp. And I want to know all the jobs, so it's dp minus 1. Index out of range. I'll stack. Ooh, what the heck? That is unexpected. Huh. Oh. Na. What the heck is this? Seriously, man. What the heck? What's temp? Huh? That doesn't make any sense. None. Oh, mass.inf times 0 is not a number. Holy crap. Wow. Okay, okie dokie. If I larger than 0, else 0. There we go. I didn't realize. Maybe we can use a really large value. Yeah, we can use a large value. We can actually see what's the largest difficulty. 10,000. So this 10,000, not 1,000 times 300. 300,000. So we can use 300,000, and then we can go back to our implementation of times int I larger than 0. There we go. Actually, this will be the most difficult. Yeah, that's fine. Oh, we got an answer. That was wrong. Ooh, shoot. Nah. We need a sentinel, man. We need a sentinel. Alright, that's okay. We need a sentinel. If dp minus 1 is smaller than math.inf else minus 1. Yo! I thought... I think we missed something. More days than then. We should do it at the beginning. Yeah, I should do it in the beginning. If n is smaller than d, turn minus 1. Okay. Well, we'll try it out. Oh! Oh! Oh, man. Man. My lord. This is bonkers. This is bonkers. Like crap. No, I won't be able to come up with this. Oh man. It has a little bit greedy in it, right? Yeah. Because we say every time we have a job based on the previous job. Yeah, the thing is we don't have to keep looking to the left. Right? We keep looking left. So every job we can include something to the left. So the question is how far we can go. We say we can go as far as the next big one. Because like add a new one will include my value, right? My difficulty. But then if we go more to the left, then we're changing things, right? We're changing things. And we are including this. We're only including that, right? But we don't keep including. Why is that? I mean, I can understand. We go all the way to something bigger. As we say, we can group those together, which is fine, right? We always group those together. And after we group those together, at the end, we also do this. Because temp stack minus 1 is the minimum up until this point. Okay, it's the minimum up until this point. Right? It's the minimum, right? So I want to find the minimum up until me, right? Then we start with some value. And then we say, okay, we can include these, right? It's the minimum up until that one. And then we say we will remove that and just add me, right? And then minimum to this and say, what if you include me? Because you're bigger than me, right? So you include me. Yeah, we don't have to keep going. Because if we keep going this one, we say the minimum to this, I say I include me. Yeah, then I cannot do because I have other difficulties higher than me, right? So we'll have to add those as well. So it's the same as just the minimum of this and add me, which basically just include me. Yeah, so for every big one, we always have a choice to include everything, right? To include everything. Still difficult. Still difficult. You know what? I probably want to do this one more time. Yeah, let's do this one more time. Delete this. Don't delete it. Let's just hide it. So we'll do it one more time. This one requires a lot more practice. We will go to default. Yeah, I'll practice one more time. Alright, maybe we can do one more. Let's say let's convert it to base 2. I want to do this one. This one seems fun. Give integer, turn the binary string representation in base -2. Turn the string should not have leading 0. So basically we're asking -2 to the power, right? Isn't that log? But can you do log -2? You can't. There's no such a thing as a log -2. Because the log, the x, has to be larger than 0. It ain't no log -2 because, yeah, you cannot say, hold on. You can, -2 to the 2 equals 4. So we say, no, this is log 2. Wait, hold on, wait, what? Log base -2. Yeah, it's not possible because log divided by log -2. That's not. It's like 10 to the something -2. No, that's not happening. Okay, so for each value, we can do this because it's just arithmetic, right? Yeah, it's just arithmetic. You know, we know -2 is just even and odd. Odd is a negative value. Cool. How do we do regular? Oh, in regular we just log it. But now it's not just log it, right? You cannot just log it. I mean, we might just go brute force for this. I don't know. Would you keep going? You keep going. They're gonna branch out a lot, man. Yeah, everyone we have 2 values. Everyone will have 2 values depending on how many positions we have. Is the answer unique? Yo, man, it's gonna branch out a lot. Well, 10 to the 9th, that's 2 to the what? I don't know, 10 to the 9th. 29th, right? 2 to the 29th, 2 to the 30th. So, what we know is 2 to the 30th, right? If everything else is a minus. You can also 2 to the 31st minus 2 to the 30th. yeah, it's still going to be a huge value. So it's not going to explode. I don't think it's going to explode. So we can find all of the possibilities. That's a lot of possibilities. Well, for one thing, right? For one thing, that all the odd position, so all those zero, all the odd position are the same. So what we can do is get all those values, right? Get all those values, because those values we already know. Let's say maybe we can convert the value into like 2. 2 is 1, 0, right? So we have a value in the even position and one value at the odd position, and then if we convert it, then that's not possible. So we need to compensate for this. So this is basically -2, right? We're going to compensate for -2. Yeah, compensate for -2. Then what we can do is do 2 to the so what we want is 2. We want is 2, but this is -2. So we'll turn this into a positive 2 by adding one more. Then we have a 4. 4 minus 2 is 2. 3 is 1, 1. Same thing. 4 minus 4 is the same. 4 is the same. Do you have more examples? How about 7? All right, 7 is 1, 1, 1. Let's say we keep this, so we just need to turn this into a +2, right? So into a +2, but I already have this. So we know this is a 3 in my case. But 1, 0, 0 is a 4. Can we add? I don't know. Doesn't look right. Yeah, 1 is 3. Three is a 4 minus 2 2. Right? What do we get? 2 times minus 2 to the 2. 2 times minus 2 to the 2. So what is 2? So 2 is minus 2 to the 2 plus minus 2 to the 1. So this come out to be minus 2 to the 4 plus minus 2 to the 3 plus minus 2 to the 1 plus minus 2 to the 0. So that's 1, 1, 1, 1. Right, 7 is 1, 1, 1, 1. Oh shit, it's not 1, 1, 1, 1. 1, 1, 0, 1, 1. Huh? Oh, we forgot a 0. Shoot. So 2 and no, we didn't forget. Oh, 4, 3. We don't have a 2. Oh yeah. Now what? You're gonna perform this type of arithmetic? Alright, let's keep 0, 1, 2, 3. Right? So we have 0, 1, 2, 3, 4. So I have a 0 position and 4 position, right? And then we minus 4. So minus 2 to the 4 is 16. So 16 plus 1 minus 8 minus 2. How do we get here? Like, seriously. How? Well, we think it has to be something minus something, right? Because they don't add up. So we have to get, like, say, 7, right? 7. And 7 is 2 to the... So what is the smallest, not integer, smallest even number that's 2 to the power is larger than 7? So 2 to the 4th, right? So now we have 16. Okay, now from 16 we want to find how do we get to 7. So 16 minus 7, we need to take away 9. Okay, I'm going to take away 9. But then how do we take away 9? Remember we have a 4 position, right? We have 4, 3, 2, 1, 0. So we set this as 1. And then we say, and all the even positions add. So the even position is either add or don't go. So when we set this, then each position we say, okay, let's minus. So this is 16, this is 8, 4, 2, 1, right? Let's say 16 minus 8. Give us 8. And then 4 and plus 4 give us 12. Nah, I don't feel right. How about multiply by 2 doesn't make any sense. I got stuck. Cannot find a good way of handling this. Okay, now we need to find a 9, right? Find a minus 9. How do we find a minus 9? Then we find the negative value with negative 8. Right? Because if negative is too big, then we cannot hit this value. So we have to find the largest value. So minus to the power will be smaller than this. So it'll be negative 8, right? So we have a negative 8. And to reach negative 9, we need a negative 1. Right? So now we have 1, 1. So now we need to have negative 1. Right? How do we find negative 1? So what is smallest that can get to negative 1? Oh, we can. Minus 2. Yeah, it has to be larger than we can add. But if it's too big, minus too big, if the minus too big, it can never be brought down. But if the minus smaller, we can always bring it back up. So should be too big. We can, well, we have too big. It's a minus 2. God, it doesn't follow the same. Hmm. Hmm. Yep, that's true. So it has to be smaller. So we get it. Oh, it's not. Oh, yeah, it is. Minus 8, right? So I have 16 minus 8 gives 8. Then we need the remaining, we need a minus 1. And this is too big, so we have this position is 4, right? Have this plus 4. A plus 4. We can do plus 4, but it's negative. Plus 4, we need to negative, that's not possible. So if it's negative, it has to be a negative value. If it's a positive value, we need to minus more to become negative, and it's not possible. If it's a negative value, it has to be a larger negative value, because if it's too small, then we cannot bring it back up either. So it has to be a larger negative value, okay? A larger negative value. But now we're looking for -1, and so a larger negative value, so this one's not good, so it's going to be 0. Okay, now we have a larger negative value, but we don't have, because this person is -2. See, like this, just the rule breaks down, right? The rule breaks down. We just say we cannot do -2. Now we do 0, then it's not possible. Okay, then we go back. That might make some sense. Right? That might make some sense. We still do 2 choices, but in certain position, we're sure the choice cannot be made. Like if the required value is a negative right now, and I'm at a positive position, then we cannot put a 1. We cannot put a positive, because I put positive, I can never get back to negative, right? And if I have a negative value and I have either a larger negative, right, or an output, I can do both, but I can choose to do the larger negative for now and then keep going. If it fails, I just swap, right? But the first value, I think the first value is for sure, right? The first value is for sure, because if the first value, right, it will be the larger value, because if you go even larger, what if you need to go even larger? Yeah, that's the problem. But if we can form every value, right, that means any value can be formed by those values added together, right? Which will mean, something plus something. Then, right, something plus something, and then 2 times. So it will just be 1 bigger at most. Right, at most will be 1 bigger than those values. And we can try. We have a lot of test cases we can try, but this stuff is tough. Yeah, we'll secure the first value, which I think is pretty obvious. And then for each position, we will bifurcate. Huh. Oh, let's give it a shot. Yeah, I think this is going to be the strategy. We will bifurcate on almost all of them, except if it's for sure it's not possible to bifurcate. Okay. Is there any DP in this? Maybe. I don't know. DFS, what are you looking for? The remaining value, the value required. So we have a val, required value, and what? Current index. How about that? Current index. It's not a current index because we go from the top to here, right? So I don't even know. I do know its position, right? The power. So we can say the P. Okay. This one shall return. How about return str? I don't know. We'll just give it a shot. Okay, so what's the end position? I mean, a 0, right? If value is 0, okay? If value is 0, then we shall return whatever the P. So it's gonna be how many P? Like if P is the power, right? If P is 3, so 0, 1, 2, 3, then it's P plus 1. So we say 0 times P plus 1, right? If value is 0. Now if value is not 0, then we take, what if value is not 0? Well, if value is not 0, then the current one we can either do, then it depends, right? It depends. We say if it's we find what is power. So we can do, in this power, we can either use it or not use it. Okay, we can use it or not use it. Let's say value is 1, right? We're currently here, and then we do the power, and if it's a negative value, I want something, now I'm saying that's not possible, right? If it's a positive, if current value is a positive and my position is at a negative position, then it has to be 0, because if it's not, then it's not possible that the remaining can reduce, right? Okay, so it will be 0. And if it's a negative, and my current position is a positive one, then it's not possible. Otherwise, we can do both. How about this? Yeah, how about just like this? If value is 0, we do this. If value is equal to, okay, minus 2 to the P power, then we return 1 plus 0 times P, right? Okay, that's that. And we say if value is a positive value, and P is a even number, right? Then we return, has to be 0, because I cannot take anything, plus DFS, same value, then P minus 1, correct? If value is smaller than 0 and P is 0, it's even position. If value is smaller, that's not possible. So we have to do this. Oh, we can just do this. They will actually both say the same. So if this or this, then we do this. All right. Otherwise, then we have to go two situations. So what is the impossible case? Well, impossible at the end. I don't see an impossible case. P minus 1. And eventually I go... Wait, what's the impossible case? So if it's 0, if this, and then we say if P is 0, and we haven't done this, right? Then return a star. This is impossible case. Otherwise, we do this. Ooh. Right, and then we say option 1 is going to be take the current. We say 1 plus DFS val. Actually, yeah, we have to go all the way to the end. We take 1, right? We take 1. That means we're gonna minus 2 to the pth power. I only need to calculate it once. Okay, so current is gonna be minus 2 to the pth power. And then we say if this is equal to current, otherwise this, blah blah. And then we'll minus the current, P minus 1. Option 2, I will say if option 1 minus 1 is, how can I say, if star is in OP1, then return OP1. We don't have to do the other one. I also return 0 plus DFS val minus, doesn't minus P minus 1. Okay, yeah, let's put let's cache this. Okay, let's try this. So we'll return DFS n. Ooh, what's the p-value? Well, I say the p-value has to be, because if it's a negative, it's not going to happen. So it has to be a positive value. So it's going to be math.log 2 p, right? And I'm going to int this. Shoot. I mean, what we can do is just go to maximum value, right? We're going to go maximum value. What's the maximum value we can do? 30, right? 2 to the 30. 2 to the 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 2 to the 30. We go 30 is the largest value. And then we just go dot left strip all the zeros. Alright, let's try the simple cases. What do we have? 2 needs to be 110. 3 needs to be 111. 4 is 100. We have 7 is 11011. Alright, let's try this one. These first. And base -2. Oh, whoa, what the hell? That is not happening. Oh, it's in. If it's not in. maybe we'll go OP2 if yeah, I'm gonna return. Not sure. Oh yeah, that take a long time. It's gonna time out, man. This is going to time out. The heck? It's going to time out. Yeah, man, it's not gonna work. 2 seconds. We can try, but this is correct, but it's gonna time out, I'm pretty sure. Unless they are very... It's 0? Oh shoot, I didn't see 0. Wait. Oh, should do this. Oh man. This, then rest if this is not equal to this, else this. Yeah, that was an oversight. But still, these just took so long. What? Oh. If res. My god, you are... Yeah, sorry, that was pretty dumb. 2 errors on the same error. I don't know what I was thinking. I do not know what I was thinking. That's pretty dumb. Oh. Let's see. Yeah, if it times out, then we will do it tomorrow. Doesn't seem to be right. The only thing that helps is this, right? And then we have to bifurcate. And apparently people don't like to go bifurcate. Maybe if we don't go from 30, right? If we really just go from, yeah, I was being lazy. That's math.log 2. I say give me a value, and I int this. Okay, I int, let's say 51, int this value, and then need to plus some value. Oh, plus this value mod. Yeah, mod 2. So it gotta be slightly bigger, right? It gotta be slightly bigger. So I think this is what we can do. We can say, let's say L equal to math.log 2 n, right? And L plus equal to 1 if L this, else 2. Then we'll start with L. I have forgot to int it. Alright, I think this might be the way. So we don't start with 30. That will be way too bad. So 3 seconds with this. Math don't. Gotta be kidding me. Alright, then we don't have to do this. We just need to return. Oh, I think this is the case. This is the case. Oh wow, we got it. Just right around the time I'm about to give up. Right around the time I'm about to give up. But yeah, this is not a good solution. I will have to check the solution for this one. Oh my god. Yeah, definitely not a good solution. But overall, we didn't bifurcate on each occasion, right? Bifurcate on each occasion. We save, but only on but still the savings from the 2 special cases where we don't have to bifurcate don't seem too big. So I'll have to check the solution for better ideas. And also limit the starting limiting the highest power significantly reduces runtime. This is all 2 to the n. Alright, now we have 2 problems tomorrow to go through. We have to rewrite this again, and we have to check the solution for this one. Jeez. Alrighty, that's about it, right? I mean, maybe we can just say, well, let me save some time. I don't know, OP minus 1 is not equal to star. Maybe. Does this one make it a little bit faster? Yeah, let's don't put this one here because I'm not sure. $5.11. Nah, it's about the same. Nothing. Alright, well, we'll deal with this tomorrow. Let's move this one higher up so we know we have 2 things to do tomorrow. Alright, that'll be it. I'll see you guys tomorrow.